All right. Hi, everyone. Welcome to Deep Learning Systems, Algorithms, and Implementation. Today, we're going to talk about implementation of recurrent neural networks, in particular, implementation of an LSTM network. As we did with the convolutional neural network example, what we're going to do today is we're going to sort of start out by illustrating what the LSTM looks like, or what just what the model looks like and the weights of the model in PyTorch, and then we're going to implement a clone of that model using just pure NumPy. And the idea here is to show the sort of guts of the implementation, and ideally also to show that it's really not that complicated. So the basic idea of the LSTM is really quite simple. So let's go ahead and get started. Here we have our blank notebook. And in the homework, of course, you're going to implement this in Needle. But here we're just going to implement it in NumPy to give you a basic idea of the operations that are involved. And then we will, in the, of course, homework, you'll have to actually use this in an automatic differentiation tool to actually run this and train these models. All right, so let's go ahead and get started. Let's start by importing Torch and importing the neural network library of Torch. And we'll import NumPy. All right, so let's start off with sort of looking at, let's put NumPy as NP. Let's start off by looking at what a PyTorch LSTM actually kind of looks like here. So let's set our model to be an LSTM cell. We're actually going to start off just implementing a single cell of the LSTM. That's sort of one block of the operation there. And the arguments for the LSTM cell are the hidden sizes for the input size is first followed by the hidden size. So let's make the input size, let's make it 20 followed by a hidden size of say 100. Okay. Let's look at the sizes that are involved in this. So let's look at there's if you look at the model here, there's actually going to be two weights that are of importance. There's going to be the weight NN and the weight the weight HH and the weight IH. To understand these weights here, let's actually go to a moment to look at the LSTM documentation that we see in PyTorch. So if you look at the LSTM documentation in PyTorch, it's actually it's a bit complicated here. They kind of write this whole thing out term by term. They write expressions for all the I, F, G, and they use weight matrices too that are like one for each pair of possible things here. But we sort of know from experience that this is not actually that complicated, right? So we sort of remember from last time, what we really said, what's going on here is that what we really have is we have sort of a intermediate hidden vector we form, IT, FT, GT, and OT. And this whole thing is some nonlinearity and happens to be sigmoid tan H and sigmoid times sort of one big matrix that multiplies really all these collections of hidden units there. So we called it WHH times HI minus 1 plus WHX X, I should say T minus 1 to XT plus we had a B, like a BH term also. Okay, that was how we defined it. And to be clear, kind of internally, despite the documentation looking like this, and by the way, this documentation bothers me for many reasons because, for example, the indices are flipped here. This should really be IH because the output is H and the output is I and the input is H, but regardless. What PyTorch is doing internally, just like we wrote it last time, is it's really combining all these matrices into two big blocks here. Okay. So what's really happening is that we have model.weights HH. Let's print the size of this. Let's see what size this is. Dot shape. We see that this is a 400 by 100 dimensional matrix. And so what's really happening here is this is actually exactly this matrix here. It's actually the transpose of that. They have it in the flipped notation, because remember, our hidden size is 100, so this is 100 dimensional. So this thing here will be, or rather this thing here will be 400 dimensional. And that means this matrix here should be 400 by 100. This one here, by the way, should be 400 by 20. And PyTorch exactly stores kind of the flipped versions of these. So this one is the 400 by 100. I guess actually, no, it's not. It's not flipped. We're going to flip it later ourselves, but to do the batch form of it. But it's exactly this matrix here. And similarly, if we look at model.weight, I guess it's what's it called? IH.shape. This is the 400 by 21. So this is actually these matrices are exactly these two matrices here. Actually, exactly these two matrices here. Okay, so we can actually look at what this looks like. So let's go ahead and now define kind of our implementation of a single LSTM cell. So a single LSTM cell, and we're going to implement this in PyTorch. Sorry, in NumPy, and we're going to check that it's doing the same thing as the PyTorch version. So let's start off by just defining the sigmoid nonlinearity. There's no built-in function, I think, in NumPy for this. So let's just return 1 divided by 1 plus 1 plus x negative x. That's the standard sigmoid function. Now let's define an LSTM cell. We're going to define this just sort of functionally, and so that means that we're going to give as input x, the input, h, the previous hidden unit, c, the previous hidden cell state. I know that really both h and the cell state c are both the hidden state, but we're going to adopt the convention of the LSTM here. And then we're going to pass a WHH, and I'll even use the WIH as the conventions. I'll forego things and adopt PyTorch's notation here, and then our bias B. Okay, so that's going to be our conventions here, and so how we actually go about forming this, right? So how do we actually go about forming this? Well, we can actually form all I, F, G, and 0 by just taking WHH here and just multiplying it by H plus WIH times X plus B. But of course, this should be O. But of course, this is now going to be a 400 by 100, 400 dimensional vector. And so to split this into 4 100-dimensional vectors, we just call np.split into 4 components. Okay. Now we have to, of course, apply the nonlinearities. So this doesn't, if we just run this, it will just be a linear function. And we go ahead and do that by applying the nonlinearities to each one. So this is the sigmoid of I. Really, these are sort of the temporary versions of I. So this is sigmoid of I. This would be sigmoid of F. This would be tan H of G, and this one is sigmoid of O. All right. And next we have the two sort of main equations really of an LSTM. So that would be these two. It would be the cell state is this FT, the forget gate, times the previous cell state, plus this term. Again, it's called the input gate times the cell gate. Again, these are just terms. They're just intermediate terms, but it's F times C. So we say that C out equals F times C, the C that was the input to our function here, plus I times G. Again, these are element-wise products, so we're just using multiplication here as you would in NumPy to denote element-wise multiplication. And then the output hidden state would be equal to O times, it would be O times np.tan H of C out. Right, and then we return the two hidden states here, return the hidden state and the cell state. Right, this actually is a finished LSTM. So let's go ahead and evaluate this, see what this looks like. So let's set X to be a random variable, a vector of random Gaussian entries, and let's make it actually just so we don't have any issues with PyTorch conversion, let's make it a 32-bit floating point number. Same for H0. That will be this random, but it'll be size 100. And C0 would be the same thing here. Oh, not copying it properly. There we go. Okay. And now let's actually look at what sort of the right answer is. I mean, let's just compute the kind of the right answer. So H star and C star by inputting this into our PyTorch version of the LSTM cell. Okay. And so this would actually be the exact same thing we were doing before. We just convert to a tensor each of these. So torch.tensor x, torch.tensor h0. Actually, the convention for these things, you have to pass sort of the hidden state and the still state as a tuple. So it'd be torch.tensor h0 and then torch.tensor c0. And that will output that sort of true h and c. It doesn't really matter what h is here. That's h, some torch tensor. And this is sort of our reference implementation of the LSTM, though. Now we're going to check our implementation against it, and we'll see that it is, in fact, the same thing. One thing I'll notice here is that I have this 1 here. That's the batch dimension, right? So in PyTorch convention for the input to an LSTM cell, the first dimension is the batch dimension. And we've implemented at least so far for just a single batch. We'll talk about batching in a second when it comes to LSTMs. And so we're just going to confirm that our output here is the same as what we got before. So let's try calling our LSTM cell with x, h0, c0, our weight. And here we'll just pass in, I'll start a new line here, but model.weight, hh, and we have to convert this to NumPy. So detach.NumPy, and then our next thing, which is model weight ih, detach NumPy, and finally the bias term. And again, torch something very weird here. So if you look at the actual documentation, there are 2 bias terms here that you add. They both get the exact same gradient. They're both just added. They're both just parameters. I have no idea why they're doing this. I guess it's not that big a deal because ultimately maybe they're matching some other weird reference implementation here. It's very strange, and I'll use PyTorch's convention to a degree, but I see no reason to add 2 separate bias terms. So I'm just going to add those 2 together. So this is model.bias. Let's see, which one is it? It's bias. Model.bias hh, and then model.bias ih. Add those together and then detach them and convert to NumPy. Right, I think that's it. Let's run this. Oops, we're getting an error there. Okay, so the size of this is wrong. Oh, of course, I have to only pass in the first elements here. There we go. Okay, and now what we can see is if we look at the difference between our solution and the kind of reference solution, which is just the 0th element of that, because this is again going to be a batch vector. We have to detach it and convert it to NumPy. All right, if we did everything right here, we should see that it's to within numerical precision. So we are in fact, and the same should be true of the cell gate. So this is all that the implementation inside of PyTorch is doing itself. Okay, it's just computing these operations here. All right, so let's now move to a slightly more complex version, because this is really just computing kind of a single LSTM cell, right? Which is not really what you typically want to do. I mean, computing a single LSTM cell is, I mean, it's worth, you have to do this, right, to test out the first block. But of course, a full LSTM, and you can in fact see this, the PyTorch LSTM class, this is the one you typically use, and it applies an LSTM to a whole sequence, not just to a single operation. Or sorry, not just to a single sort of hidden state and output state. You really apply it to the entire sequence there. So let's take a look at that and see how this would do. So now let's talk about sort of a full sequence version of our LSTM. All right, and how will we implement that? Well, let's start with redefining our model to be PyTorch's LSTM. And LSTM, for some reason, I believe, if you look at the docs here, the arguments are the input size is first and the hidden size is second. So unlike LSTM cell, for some reason I can't really understand, they have the hidden size first and the other size second. Or actually, is that right? Sorry. So it's the input size first and the hidden size second. So that would be 20, 100. Whereas this, oh no, actually this is the same too. Is this the same? Okay, yeah, so it actually is the same. I thought maybe it's a different one I'm thinking of. So anyway, yeah, LSTM has the hidden size and the input size, and then the num layers is an argument, and we want num layers equal to 1. Okay, and so this is now a single layer LSTM, and as before, we can run it on some data, but here we're actually going to run it on a whole sequence of data. Okay, so rather than running it on sort of a single input, we're going to run this on a whole sequence of inputs. I'm going to denote that or sort of emphasize that by making sure that we use uppercase X here to denote a sequence of, say, 50 different time steps. So now each of the rows of this matrix is going to be a different time step. And the C0 and H0 and C0 are still just one-dimensional, of course, because they are just the initial state into our LSTM, right? This is sort of what we're doing here is we are computing an LSTM, which remember takes in sort of an H0 and a C0, uses this along with X1 to compute H1 and C1. Then uses this to compute H2 and C2 along with X2, etc. Okay, so we're gonna write the code that implements this now. All right, so everything here actually looks very, very similar to before. Well, actually, I should take that back. It's just leveraging the same cell we had before, just applying it in sequence one after the other, right? So that's all that's really happening here. So let's define now, rather than just our LSTM cell function, let's define our LSTM function. So let's define LSTM, which will take in this input X, still H and C. Those are the sort of the initial states there. Same inputs as before, WIH, WHH, and B. Okay. First thing we're going to do is we're going to initialize kind of our set of all our hidden states. And actually, it turns out that we're going to kind of follow PyTorch convention here, where we're only going to return the array or the sort of the tensor of all hidden states over all times for the H variable. The C, the cell state, we will just return the very last one. Okay, so that's just sort of convention. PyTorch, for again, kind of owing to the convention of an LSTM, does not return the whole cell state. It just returns the whole hidden state portion of the hidden state, and then the last cell state. And we'll see actually at the very end of this lecture why we return the last hidden state. All right, so H is going to be equal to let's start initialize it with zeros. So the zeros should be x.shape 0, so we want the same size as X, but then the output would be the same size as H, right? So H, it'll be the number of rows in X and the number of columns that are in the size of H. Okay. And now we're just going to iterate over our whole sequence. So for T in range X shape 0, we run our LSTM cell. So we set our hidden state and our cell state to be equal to the LSTM cell of xt, so just take the teeth element of that, h, c, w, h, h, w, I, h, and b. And then we're going to set ht to be equal to h. Okay. And we're going to return the tensor, really just matrix here, of all our hidden states and the last cell state. Okay. All right, so now let's, again, kind of run our LSTM first. Actually, the call is going to look very similar to this. I'm just going to copy this thing here. Going to copy that and input here now my whole X, just the first hidden state. I'm still using the convention, again, for PyTorch's sake, that, you know, we have a batch of these things, even though we'll, again, get to batches in a second. I'm going to pass this as our inputs there just for simplicity, and we're going to call this instead, though, LSTM, and we're going to get the set of all the outputs. All right, so this is our call to our LSTM. Make sure that all runs. Nope, what are we doing wrong here? Right. So the model does not have any more of these terms anymore. Actually, what the model has is weight HH L0, because it's the 0th layer. Actually, I'm going to replace these all with L00, L00, and the same for the biases. So it has to replace L0 bias and L0 bias. Okay. And then it computes. Okay, so now let's just do the same thing for talking about the sort of the reference solution. Actually, PyTorch returns both the full matrix of hidden states and a tuple containing the last hidden state and the last cell state. So I'll say like the last hidden and the last cell. I'm actually call this C. I should call this more like CN or something like that, like the next hidden state or something. And this is going to equal the model applied to the tensor of X. Let me just go up and copy what I had here. Tensor and these things. And if you'll forgive me one bit of trickery for now, I'm going to do one more thing here. I'm actually going to insert an extra dimension in there in the second dimension. And we will immediately come back to that in the next section while I'm doing that. But just know that for now, you have to add a 0 dimension in the second dimension, or a 0 sort of column of size 1 in the second dimension here for this to actually match. So I'm going to do this. And that should work. Nope. Close my brackets. And now we can similarly print the difference between, let's just print, whatever, I won't bother with the print, np.linealg.norm of h minus h. And we want to similarly just take this first entry there, dot detach. All right, and let's see what that looks like. So again, we're within numerical precision in our implementation. So the LSTM model in PyTorch is exactly just calling this thing. And we're just implementing it in NumPy now, but you can of course implement the same thing as a module in Needle, and you'll have a module that does the same thing as your PyTorch LSTM. And this is true with one little exception here, which is I'm not going to come back to this weird batching now. Or this weird sort of extra dimension that I have here, and talk about that. And the reason this all comes up, and sort of what's going on here, what's going on here is related to how we batch LSTMs. So I want to talk a little bit about kind of, again, kind of in theory about, now that we've seen some discussion about sort of efficient implementations also when it comes to sort of the I guess you would say like the internals of matrix multiplication, we sort of know that multiplication works best when matrices are contiguous together in memory. In fact, in Needle, the only way that we can really run matrix multiplication is by first compacting the matrix, then calling multiply, and then having that compact matrix be the thing that we multiply. And so if your sort of memory is scattered all around, then it's really sort of unclear how you go about doing the multiplication. And this relates to this sort of what's happening here. So let me kind of dive into this a little bit more here. In some sense, for the case we talked about before, we have this setting, right, where we have a matrix X, which we defined as being basically T by N, or I guess D, where D here is the size, the dimension, the hidden dimension. Sorry, I guess X is N, right? X is the dimension of the input, and T will be the sequence length, right? That's how we defined our X input here. So now the question is, suppose that I want to process multiple batches of this at once. Because the problem with this, of course, right? The problem with this call that I'm doing right now is that even though I'm processing kind of a matrix of x's as input, I'm still doing matrix vector products in my LSTM cell. So, right, so my LSTM cell call is still calling individual, this hidden state at time t is still a vector, right? And that, of course, is really sort of fundamental to LSTMs. You can't, these things are vectors, right? And so you can't compute H2 and C2 until you've computed H1 and C1, right? We'd like, in some sense, to be able to compute all of these simultaneously in one big batch, but we can't do that. These are vectors, and the only way to compute these things is to do a matrix, i.e. the weights of our LSTM, times this vector, right, for each sort of slice of time. And we don't want to do that, right? Of course, we want to really do matrix operations. That was sort of the whole crux of our linear algebra work that we did, and we saw that matrix multiplications were much faster than matrix vector products. And so the question is, how do we go about doing that? Right? So how do we go about? We would like to batch these somehow, right? To add another batch dimension, and we want to ask kind of how would we go about really doing this? Well, kind of the most obvious thing we could do is take our matrix here, which is sort of, has the number of times and the number of dimensions, and add a batch dimension like we are used to, right? Just add a batch dimension, which just describes the number of examples in our mini batch. And we can do this, and this is sort of this would be kind of normal PyTorch conventions for how you set up a matrix, right? And in convolutional networks, the batch dimension is always first. In MLPs, the batch is always first. It would make sense for the batch to be first here. But let's sort of think about this again, right? If we are laying out our memory in this form, and then we access kind of this element here, right? So if we want to access all the elements at time 1, that would be kind of this call here, right? Call like this. And unfortunately, if we're storing our X matrix, and the same goes for the hidden states too, if we're storing our X or our hidden states or any of the other terms in this form, then a matrix like this, which again is sort of all the inputs at time 1, this would not be contiguous in memory, right? So if we want to do, just a batch form of these expressions here, apply them to a multiple element of these expressions here, apply it to a whole matrix, we'd be inputting as X and then eventually as H some matrix that looked like this, right, for different t's. So we do this, t equals 1, t equals 2, etc. And that would not be contiguous in memory. And so for that reason, when we batch things in for input to an LSTM, we switch this around. We actually, kind of breaking convention, store the time dimension first, then the batch dimension, then the hidden state dimension, or the input dimension, or the hidden state dimension. All right, and you can actually see this in the documentation for PyTorch too. So PyTorch will talk about kind of the format. It uses, I guess it uses N for the batch size, L for the length, and HII for the hidden dimension. So a little bit different, or H in for the input size, H out for the hidden size. But normally speaking, this will use this format, unless you pass this batch first equals true flag here. But this is actually not the standard convention, and you shouldn't do it this way, at least not naively if you're using kind of a traditional matrix multiplication routine, because if you pass kind of this form of batch matrix, you would end up having to process a whole lot of matrices like this, which are not contiguous in memory, so you have to copy them over anyway before doing the matrix multiplication. Okay, and that would not be a very good thing. So it's much better to input it in this form, and I guess in PyTorch convention. So if you, this was TB, and it's like in PyTorch convention, this is what they call this, I think. They call this LNHII. LNHII. No, H in, right? So sorry for the little different use of notation there. I think we've used this throughout the class, so we'll keep doing that now. But this is what they call it in PyTorch. Okay, So this is how we're going to pass matrices in. And the nice thing about that is once we do that, we can just use a call like this to get all the batches at time t in a nice contiguous format. All right, so the only difference now is that we need to, when we do this, we have to use a slightly different definition of our LSTM cell, now designed for batching. So just to emphasize this, I'll sort of give a set of these things. So actually, you know what? I'm not going to bother with that. I have to change them a bunch of places, so I won't do that. But what I will do is define these sort of separately. So what we actually have here would be H times WW. Our convention is that actually this form is the actual form of the matrix. The other form was a transposed form. So we're gonna keep that as the form we actually care about. But this is sort of our convention here. This form, right, was the form we care about. Well, similarly, we'll say X times XWIH. We'll then have to actually transpose the PyTorch internal arrays to get them to look like this. Probably I really should have written originally like this, because we typically said that when we multiply as matrix tens vector operations, we transpose them. But whatever, I already wrote it like this, so that'll be okay for now. But I'll transpose our weights before this. Everything else the same. The only difference is we actually have to specify which axis we're splitting over. So these are all going to be matrices now, and we want to split over like in normal sort of convention, the first dimension is going to be the batch dimension, second dimension is going to be hidden dimension, so we want to split over the second dimension, or axis equals 1. Everything else should stay the same. Because these are all element-wise products, we actually don't need to change anything here, so we get the same exact form. So let's just redefine our LSTM cell like that. And I think we actually can keep our LSTM even the same as before, but let me just make sure that's true. Where's our LSTM? No, we actually have to do a little different there. You have to define the size of our hidden state to be different. So now our hidden state would be, its first dimension would be x shape 0, but this is now the time dimension. The next is going to be the batch dimension, like this, and then h is also two-dimensional in our convention, right? So the first would be the batch dimension, second would be this dimension, so we want this dimension of the second dimension of h. Now we want to go for t in all the time, which is still the shape 0. This is still the total number of time steps. H and C equals LSTM cell. That's all the same as before. And then HT equals T. And I think this all stays the same as before. Okay, so now let's go ahead and test out our batch version of our LSTM cell. Let's create some data. Let's say, again, we're going to have 50 time steps, but now let's add a batch size of 128. And of course, it means we also need to have 128 different initial hidden states and 128 different initial cell states. And we'll leave the last dimension here just for the sake of PyTorch. Okay, so I think that's about it. It's actually even easier than before because we don't need to play this weird game here with tensor shapes and everything. We have all our dimensions for PyTorch to be happy. So let's input H, H0, and C0. And let's see, okay. And now let's make our call. So let's take our call of our hidden state and our next set of cell states, make this an LSTM. We still have to say 0 here because we still have this weird, I guess that's now a batch dimension. It's very odd how PyTorch does these things. This is like, I guess a sequence dimension here. So, you know, we have a sequence only of 1 for the hidden state, the initial hidden state, initial cell state, but we'll pass in zeros for those. We do have to transpose these. So by our convention now, these weight matrices are transposed versions of their old selves. And I think this is it. Let's see if that runs. Okay, great. Now the big moment of truth here. Let's see if, in fact, these two things correspond to each other. So let's find h minus h, detach, numpy. And, oh no, So the H, which one would it be? Let's see what shapes they are. Okay, so that's that shape. Let's see. So the same things. Oops. There we go. Okay, and as long as I don't call, a module by accident, I'm trying to call a norm, everything works. So these things still work. And we have now a full implementation of a batched LSTM, exactly the same sort of mirroring PyTorch's implementation to numerical precision, in, what was that, like 10 lines of code here, 13 lines of code. Not too bad. And I could abbreviate it more, right? I could cheat some and like make it even shorter. But the point is, this is a really, really simple operation, and sort of the mathematical form might look a little bit hairy there. I mean, sort of, looking at these equations, it probably would take, more lines of LaTeX code to write this code out than it takes just to write it in code itself to actually implement this. So that's pretty nice, right? Okay, now that actually is the majority of what I want to talk about that I'm actually going to evaluate here in the notebook. That's sort of the majority of what I can validate and check here without having an automatic differentiation tool backing this whole thing. But I want to talk a little bit, just sort of writing the code, but not being able to run it because we're not going to write this in Needle, about training LSTMs. I want to just kind of conceptually talk about what does it mean to actually train LSTMs, and in particular, there's sort of there is one sort of subtlety when it comes to training them, which I'll talk about a little bit. I alluded to it last time, and it had to do with something called truncated backpropagation through time, but we'll get to this in a second. So, all right, let me first talk about how we might train an LSTM to accomplish some task, right? And the basic idea is that I want to be quite sort of simple and straightforward here, and sort of define a routine like train LSTM that will take as input X, H0, C0. So that sort of is the input to run the LSTM, but then we'll also take Y, which is going to be like the target output of our hidden state. Now, in reality, what you really might want to do is have an extra layer on top of the LSTM that actually computes, a projection to the same dimension as Y or something like that. But I'm going to ignore that. Or rather, what I'm going to do is I'm going to sort of bundle that all in some loss function. So I'm going to give it a target Y, and then WHH, WIH, B, and then something like an optimizer. And this is all conceptual, so I'm not going to worry too much about the details here. Now, what I would do to train this LSTM, the nice thing about this is that this is incredibly simple. So I would just basically call H and Cn equals my LSTM of X, H0, C0, WHH, WIH, B. All right, so I just would call my LSTM. And then I would compute some loss between my hidden state and my target output. And that could be a loss that involves, one more transformation of the hidden state by another linear layer or something like that. I'm not going to worry too much about that. Or it could just be trying to directly predict the hidden state from, or the Y from the hidden state. It's something, but it's some loss function, sort of a simple loss function, just compares each sort of individual H and each Y. And then, in the beauty of automatic differentiation, if I've implemented all of these calls in Needle, right? So if I just replace this NumPy implementation with an implementation in Needle, and you have to add a few more things to this, by the way. You have to add, which you will do in the homework, is add things like split and stuff like that. You have to add support for that. And I mean, 10H actually isn't too bad because we already have exponential. So. As long as you do all that, implement it in Needle, then to get the gradients with respect to all your parameters, you just call loss.backward and opt.step, right? Where opt here would be like an optimizer setup. Opt would be something like SGD with the parameters is equal to like WHH and WIH and B or something like that. It's just, again, this is just sort of an illustration. I'm not gonna, this code will not, of course, run. I guess that will run. I'm defining it, but it will, I can't call it. Okay, so that's sort of how I want to set things up to start with. The next thing, the only last thing I want to say about training is that if we have a deep LSTM, so suppose we have an LSTM that is multi-layered, right? So we have, you know, H0 for the first layer, going into H1 for the first layer, go to H2 for the first layer, etc. And this takes X1, this takes X2. And then I have some other layer here, so H2, oops, 1, and then H2, that was actually correct, H2, 2. And then I have some initial hidden state here, H0, 2. Here I'm actually going to forego the LSTM, the cell state portions. I'm just going to talk conceptually about a deep layer here. There actually, I have a little bit of options here now, right? If I want to compute this element here, I actually have everything I need to compute the second layer for this time after I've computed this element here, right? So I could compute kind of this whole thing layer by layer and then compute it sort of time slice by time slice. So I could iterate kind of layer by layer and then iterate time by time. But because the LSTM call calls an LSTM over a whole time sequence, it's much more common to sort of compute this whole layer here and then use that to compute this whole layer there for a deep multi-layer LSTM or a multi-layer RNN in general. All right, so that's what I'm going to do here. I'm going to define, you know, a function like train deep LSTM, and I'll have x, y, or x, h0, c0, y. These would now be, I guess, arrays of all my h0s and all my c0s, right? And then I would have w, h, h, w, I, h, b. These are now going to be lists or tensors of all my different weights. And then I'll still have opt, which is like over all of them. And so what that would be is I would have something like, actually, I'm gonna, yeah, so I just set the initial state actually even just to x for convenience, and then the initial input to the first LSTM is of course x, and then so for d in range depth, I guess like depth equals something like the length of WHH or something like that. You would say that H and Cn equals LSTM applied to H0D, the dth element of that, C0D, and then WHHD, WIHD, and BD, right? Again, this is all conceptual, so I might be making a typo here. Hopefully not, but we would finally compute some loss between our output and the input there, or in the target there. L equals some loss, and then we would just say L dot backward and op dot step. Okay, so that would be our training of a deep LSTM. Okay, and that actually is it for training, except for one sort of subtle but actually very important point that comes up when training LSTMs, especially on very long sequences. So let's suppose that you had an LSTM to train, and you want to train it over a sequence X. It goes from X1, you know, X2, all the way up to X, like 10,000. You could just do this. Now I could call my same call I had before, but it would probably run out of memory, right? Because I'm creating, you know, I have to maintain all memory around, because I'm running here kind of running this all in AutoDiff framework. I have to keep around kind of all my intermediate states so that when I call loss.backward, I can propagate through all of it, right? And that's not very good. Right, that's sort of a bad thing. That's definitely going to be kind of sort of a suboptimal thing, or we just can't do it. And so there's a few options, right? We could try to use a smaller network, just use smaller sequences, whatever. But the most common thing to do is to run, again, what's called backpropagation through time. So those training routines that we had, computing the gradients, taking a step, that's called backpropagation through time. But what we can do is just, and what we can do with this procedure, instead of running it through the entire time sequence of 10,000 examples, we just take some length, like 100, and just sort of truncate there. So there is obviously an x101, but I'm going to call my LSTM only on the first, and compute the loss only on the first 100. Okay, so again, I'm just going to write this down in terms of a generic RNN, so I'm only going to have one hidden state, and even a single layer one. All right, so I generate those, and I make some predictions from that. But the point is, I'm going to create my RNN with just the first 100 time steps, and I'll use like H0, normally like I would of all zeros or something like that, because that's the start of the sequence. All right, so I just truncate things, and I run my loss there. And now I move to my next sort of subsequence. So let's say, something like 100 to, hiding that there, but fortunately it's not too important. So this would be 101 to, say, 200, right? And I truncate again. So I compute, my H101 to H200, and I compute my loss based upon this, and I just do that. This is a procedure, kind of generally speaking, called truncated backpropagation through time, because you take your whole sequence and you just sort of chop it into chunks and train the LSTM on these chunks. Now, you're rightfully would sort of be right to kind of question whether this is a good idea or not, right? Because, after all, there's a really important connection between those two things. You're just ignoring it here. You're just sort of throwing it out entirely. And so this seems like a really bad idea. But the reality is it's not that bad an idea. Even just doing this, where you just ignore entirely, just chop it up into independent chunks and just train it entirely separately, that actually works probably okay. Things aren't too bad. But we can make it just ever so slightly better than just that. And what we do to do that is a technique called hidden unit repackaging. So the idea here, the core intuition here, is that when we started our LSTM, we started at this H0, which is just, say, equal to 0, right? We just initialize it, say, with all zeros. And when we trained this first portion, we just called it with the H0. Again, this is sort of, and by H0 here, I really mean, this H0 fed into this function, right? That was just this zeros at first. But then the question is, when I feed in my H0 for this portion, for training this next portion here, what should I feed in as my H0? I could feed in 0 again, right? I could just treat the H0 again as 0, so basically you would do something like, feed H0 equals 0 into there. That would be fine. But we can do something a little bit better, right? We know the value of our hidden state, and when for an LSTM, we know both the hidden and the self state, of course. It's just this. We know sort of the last value of the hidden state in that sequence is just H100. And so what we're going to do in what's called hidden unit or hidden cell or hidden unit repackaging is we're going to take this value and we're going to copy it into the H0 for this next sequence. Okay. Now, importantly, we are not, I'm going to draw this in like red or something like that. We are not actually creating one big long compute graph through this. What we're actually doing is just taking the value of H100 and feeding it into the initial value of our next sequence. because of this, no gradients flow through this. So we don't get a sense of, how will changing the weights affect how x100 affects h101. But we do see for the previous weights, right? For the previous value of the weights, how is that x100, whatever effect it has on h100 is propagated through. For those that have seen sort of similar calls before, this is also called a stop gradient call and things like this. You basically keep the value of your last hidden state as the initial value for your next sequence, but you don't propagate the full compute graph through, right? And that's the idea of hidden unit repackaging. So what that looks like is actually very simple. What that looks like would be something like the following. And you can actually even call it like you would with you can call it by sort of calling these training procedures as subroutines now. And the way it would kind of work is you would first define the initial H0 and C0 as zeros of some dimension, right? Actually, I'm gonna now officially abandon all attempts to write proper code here. And what I would do is I would sort of block my whole sequence into some number of blocks, right? So I would say something like, rather than iterating over my whole time, I would say something like for I in the range of the number of blocks I have, that's the total number of dimensions time divided by the block size. Maybe I'll even write that. So like, this is like sequence length divided by block size. And what I would do is I would say, I'd do a few things, first of all. First of all, I would actually sort of store the old hidden states here. So I would actually do something like store the hidden state I, or D rather, would be equal to the last value of the hidden state here. This is dot detach and dot copy or something like this, right? So I'm going to detach it from my compute graph and then just copy the value. And then same for the hidden, the cell state. So this would be cn.detach copy. This is, by the way, why PyTorch returns the last hidden state and the last cell state for the LSTM, so you can detach them and repackage them for your training procedure. And then I would something like return my hidden state and my cell state. Okay, so now in my training loop, I would sort of keep track of these things in my train deep LSTM, and I would feed into it not the entire sequence, but just like the sequence of I times the block size to like I plus 1 times the block size, right? And then H0, C0, Y with the same size here. And of course, I could also include a batch dimension. I mean, this is just the sequence dimension, right? So this is like the first dimension. There, of course, also are batch dimensions after this. And then something like the WHH, WIH, B, and opt. Okay. So again, this is just sort of conceptual. Put this down here. But hopefully this conveys kind of the notion of what you actually mean when you want to really train a LSTM on, or really any RNN on a large sequence like this. What you want to do is you want to split it up into different blocks, and you want to train each of these blocks, with gradients flowing through for just the block size. But then rather than start completely anew with a brand new hidden state, you start with the previous hidden state and the previous cell state for an LSTM, just a version that is kind of detached from the compute graph. So you're just really copying the value, not the whole graph. Okay, and that is about what you need to know to implement the LSTM on your homework 4 assignment. So next lecture, we're going to move to our last sort of unit on different architectures in deep networks and talk about transformers. So see you all then.